Hello Math 4411 students, here's lesson 11, Rings and Fields. We completed the group theory as of last week, at least within the curriculum of Abstract Algebra 1. If you went through the textbook, by the way, you would have noticed that there are still some advanced group theory topics left uncovered in our textbook, such as Sylow theory, Cayley's theorem, normal sequences, solve-over groups. Oh my, there are a lot. But all those are going to be dumped over to Abstract Algebra 2. For us, that's enough. Enough is enough, and we're going to move on to the next topic. Yes, we went through groups. So the next item in the list, rings, and then fields. By the way, this one here, the next one here, vector spaces, this is going to be covered in linear algebra, Math 3315. So let's not worry about that. And as for these two, modules in algebra, again, Abstract Algebra 2. Okay, let's come back. Here's the definition of a ring. A ring is a non-empty set with two binary operations. Not just one, but two. And with respect to the first operation, we have the abelian group structure. So we typically use the addition notation, and we're going to call it the addition. And also, the additive identity is typically referred as 0. But if you don't like 0, then you can use some other character like this if you want. And that's fine with me. And that's it for the addition. Now, how about the next operation, which we're going to call the multiplication? Well, we impose just one condition, the associativity, and that's it. And then we have two operations, so the natural question is, how are they related? Well, here we go, the distributivity to the left and then to the right. Now, please recall that we only have the associativity. If we had the commutativity of multiplication, then these would have been redundant. I can always switch the order of multiplication, but in general, we can't. So we need both of those two in general. Now, speaking of commutativity, yeah, it doesn't belong to these standard 6 properties that'll make a ring, but we can regard it as an additional condition that gives us something more specific. A ring that satisfies all those 6 properties, and in addition, this one as well, the commutativity of the multiplication, is called a commutative ring. We do not use the term abelian ring. The term abelian is used only for groups. For rings, commutative rings. So if you have a commutative ring, then you don't need both of these two. You can leave one of them out. Now let's take another viewpoint. Let's consider the multiplicative identity, but there's actually a bit of a wrinkle here. It doesn't work for 0, the additive identity. In fact, you can prove that 0 times anything is 0. And we'll prove it actually shortly, maybe in the next week. The next video, not next week, next video. We're going to prove it. Consequently, we cannot consider the multiplicative identity or inverse for 0. So let's consider it out of our picture, and let's consider only the non-zero elements. Then we can consider the multiplicative identity, and we're going to call it the unity. So if you have two identities, that's a bit confusing. So the additive identity is 0, and the unity is kind of like 1. So if you don't like to use this U notation, yeah, you can just use 1 like this, and then 1 times 1 times x is x times 1 equals to x. You can rewrite like this too. So not all rings have a unity, but some rings do. And not all rings are commutative, but some rings are. Now, if there is a ring that is both commutative and also have a unity, we call it a commutative ring with unity. Now, on top of those, if you have this additional property, a commutative ring with unity with no zero divisor, then such a ring is called an integral domain or a factorial ring. Here's an example of the application. How do you solve a quadratic equation? Well, factor like this, x plus 2 times 4x minus 5 is equal to 0. And then please recall that there is no zero divisor for polynomials. So the polynomial ring, as a matter of fact, will turn out to be an integral domain or a factorial ring. So blue times green is 0, so either blue is 0 or green is 0. So x plus 2 is 0 or 4x minus 5 is 0. So from the first equation, blue equation, I get the first solution, x equals to -2. And from the second equation, from green, I get x equal to 5/4. See? That's a thing that we used to do from way back, actually. Way back. And this zero divisor property, or no zero divisor property rather, that's highly useful property. But the fact of the matter is, not all rings satisfy this. Some rings do, and such a ring is called an integral domain or a factorial ring. Our textbook author calls it an integral domain, so I'm going to use this term more often. But as for the second term, factorial ring, well, here's a motivation. This kind of technique is called a factorization, right? That's why it is called a factorial ring. But I'm going to use the term integral domain more often. Let's see, we went through all kind of rings and subcategories, excuse me. Can you think of some examples? So, two algebraic operations, addition and multiplication. Well, here are some immediate applications. The set of integers. We have addition and multiplication, but not necessarily a division, you see. And subtraction is okay because in terms of addition, we have the additive inverse property. So adding the inverse is a subtraction. So subtraction, no problem. But as for the multiplication, well, we don't have inverse in general. We don't even have the identity in general either, actually, or the unity rather. Another example, the polynomial ring. Set of all polynomials with real coefficient, and this one here, if you don't want real numbers as coefficient, you can change it to complex number system or rational numbers. You can do various things. In any case, the set of polynomials with all those induced operations form a ring. And as a matter of fact, in this case, they're both integral domains. They're both commutative, yes, that's clear. And they all have the unity, 1. Z has 1, of course. And how about the polynomials? Yeah, we have constant polynomial 1, so yes, we have the unity. And as for zero divisor and factorization, yes and yes. Now, can you think of some examples that some of them fail? Some non-commutative rings? Can you think of something? Non-commutative rings, which means yes, we have to have commutativity with respect to the addition, but not with respect to the multiplication. Can you think of something? I think by now a lot of students must have thought of this. The matrices. If you have all those square matrices, then you can add freely because the sizes are all the same, and then the multiplication is well defined, yes. And then we have the unity, the identity matrix I, ones through all those principal diagonal, everything else is 0, yes, the identity matrix, but no commutativity. Okay, all right. And all these, by the way, are rings of unity. So this one is non-commutative, but still rings of unity. Now, my challenge. Rings with no unity. Can you think of that? Rings with no unity. So we have 1 as a number. Here we have 1 as a constant polynomial. Here we have I, the identity matrix. They're all unities. Rings with no unity. Can you think of that? Well, stop the playback and think of those. It's not easy. Well, okay, all right. Have you thought of something? It turns out, there you go. Set of all even numbers. Well, please recall that they're all closed under the addition and multiplication. Even number plus even number isn't even. Even times even is even. So it's closed under both operations. And as for all the other properties, yeah, you can check. But no unity. 1 does not belong there. And you can do the same thing using the even numbers to matrices. Set of all n by n matrices with even integer entries. If you don't like even numbers, well, why don't you use multiples of m, for example, multiples of 17, all those kind of things. Yes, you can create all those kind of things too. All right, we went through rings, but one thing that is missing, completely missing about the rings is the multiplicative inverse. If you have the multiplicative inverse as well, that thing is called a field. So we have the associativity to both multiplication and addition, commutativity to both of them, and distributivity to both of them, and in this case, due to the commutativity, the second is unnecessary. And the additive identity and the multiplicative identity, or unity if you want to call it that way, and the additive inverse and multiplicative inverse. We have 1 over x as well. That kind of thing is called a field. For example, the set of all real numbers, the set of all rational numbers, set of all complex numbers, all those kind of things are fields. You can do divisions as well. Now, what if you have, say, general linear groups, for example? We have invertible matrices, n by n matrices. Yes, we have multiplicative inverses as well. So the general linear group, does it form a field? The answer is no. We don't have the commutativity of multiplication. By the way, here's a summary. Field, integral domain, commutative rings and rings with unity, and general rings like that. Okay, so much for the general definitions.